Afternoon, ma'am.
Good afternoon, sir.
So shall we start?
Yeah, I'm ready.
Okay. All right. So I welcome everyone today to this 10th day of the FDP on quantum communication. Today we have one of the eminent speaker in the area of quantum computing. She's also playing key role in National Quantum Mission. So I'll give you a brief introduction to her. Dr. Anindita Banerjee is a senior quantum technologist at CDAC Pune, where she leads several strategic initiatives in quantum technologies. Her current work focuses on fiber-based quantum key distribution, quantum random number generators, and aerial quantum communication platforms. In the domain of quantum computing, she is actively engaged in developing diverse application on accelerated platforms. Before joining CDAC, she served as quantum research head and vice president at QNU Labs Private Limited, where she played a pioneering role in advancing quantum safe cybersecurity solutions. At QNU Labs, she led the development of India's first fiber-based QKD system, taking it from TRL2 to TRL6, and successfully implemented distributed phase reference protocols for QKD in fiber systems. Her work also encompassed theoretical security proofs, simulations, and key rate analysis. Additionally, she developed India's first QNRGs, including a time of arrival based QNRG and a hybrid QNRG system. Her academic journey is equally distinguished. During her PhD research, she designed novel quantum communication protocols and worked extensively on quantum circuit synthesis and optimization. As a postdoc fellow at the Bose Institute, Kolkata, she established a quantum optics lab and carried out foundational experiments in the field. Many of the technologies she has developed have been successfully tested by both government and industry organizations. Her contributions have also been recognized through 4 US patents and 1 Indian patent, highlighting her ability to translate academic research into impactful real world products. She has published several well cited research papers and co authored a book with Professor Anirban Pathak titled Optical Quantum Information and Quantum Communication, which continues to serve as a valuable reference for students and researchers. So we are honored to have you here, madam. And now I request request you to take the control of the session. Thank you.
Yeah, just before ma'am start, just I want to add one sentence. She is one of the committee members who are instrumental in framing the syllabus for this minor degree by AICT. She is one of the committee members. We are privileged to have her as she's extensively, as Dr. Mitarwala has already introduced, she has extensively worked and a lot of motivation she has given in the earlier courses as well. And she has given an industry perspective. So we are looking forward, and she has also agreed to give us a demonstration of some of the key distribution protocols that we are looking at. So let's look forward to a very inspiring and challenging session. And over to you, Dr. Anindita.
Thank you so much, sir. Thank you for the kind introduction, and welcome all the teachers. It's an honor to present work in front of you. And so here we start without wasting too much of our time. I think it's the topic is very big, but we have got limited time. And we will try to bring it to you as a story. And later, if you would want any material or now we also have some standard books, some books also in quantum communication. There are a lot of reference papers also there. So let's begin. So quantum cryptography, QKD stands for quantum key distribution, one of the application areas in under quantum communication. So we know that the human desire to communicate secretly is as old as writing itself, and it dates back to the beginning of civilization. In past, several ancient societies had developed this art of secret communication. Some of the interesting cases are the Spartans around 400 BC. The Spartans had pioneered military cryptography in Europe, and they used a device known as Skytail, and that used the method of transposition for encryption. Then came Caesar cipher. Julius Caesar he used to use in his correspondence substitution method, okay, which is known as Caesar's cipher. Then around early to mid 20th century, Enigma was used. This is a electromechanical cipher device used by Nazi Germany during World War II for military communication. And Alan Turing had developed an electromechanical tool to break this cipher. So we all are aware that this led to the establishment of first digital computer, Colossus. So now we are moving towards modern cryptography. So modern cryptography was born with computers. Now here today the encryption, if you look at this entire quantum safe encryption is one aspect, but this is basically the standard architecture for any cryptography. You have encryption key, encryption algorithm, the plain text, then the key, and then you have decryption key, decryption algorithm, plain text. Okay, and this is how the communication is taking place. So today the encrypting algorithm and decrypting algorithm is publicly known, and this does not compromise on the security of the cryptography. Today, the security of the cryptography lies in the secrecy of the keys, encryption key and decryption key, because the key goes in with the message or the plain text, and it also goes along with the cryptogram in the Bob's side. So Alice and Bob are the cryptographic couple. We can say sender and transmitter also. In QKD, we'll say node 1, node 2. Okay. So this is a standard method of doing cryptography. Now, what would be the best encryption algorithm? Let's talk about the Verman, the one-time pad. So according to the Claude Shannon, as long as the key is of the same length of the message and the key is truly random. Now I know there will be questions on how do we define truly random, but there is a way of guaranteeing that it is random enough. Then this cipher is believed to be forward secure or unconditionally secure, theoretically secure. Okay, so then what's the problem? Okay, so we already have a solution, but here there is a snag, which lies in the key distribution problem. So it is a key distribution, which is where there is, as you can see in the picture, there is an eavesdropper who is trying to look into the communication channel and trying to find the key which goes along with the cryptogram, or we'll come to the PKI infrastructure as well. But what is the key distribution problem? So in principle, the classical key distribution can always be passively monitored without the Alice or Bob or legitimate users coming to know about it. Okay, so this is the problem we are trying to solve through quantum communication. So here again, please note that when I'm saying key distribution, I am actually having the key and I am distributing it to my partner. Alice is sending the key to the Bob, and this happens in the classical world. It is very important to understand this because there is a deviation from the word quantum key distribution. In classical key distribution, again, I'm saying you have already generated the key and you are distributing it from one point to another point. That is the key distribution problem. Now, if you're looking at this scenario, what would be the ideal rules for security? As I already mentioned, that in today's world, the security is as good as the key itself. So that is one of the challenge, that the key should not be copied. It should be random enough. And if somebody has tried to monitor the key, then I should be able to take action, or there should be some stamping available that this data has been monitored or it is adulterated. Some kind of a signal should be there, and signal is only possible if I can identify, but that itself is a problem. So fine. So we all know about the classical scenario, but here again, I would like to take your attention to the computational problem, right? Computational security. In quantum world, we'll be talking about the information security, information theoretic security. So, so now if we try to approach the key distribution problem, we will take it in two ways. One is trying to look at it from mathematically, and the other through physically. Now, mathematically, if we are saying, as what happens in the present digital world, that we are concerned with the computational difficulty of solving the problem. So the problem statement is actually carrying the key. So we are looking at the computational difficulty of breaking the code or performing a computationally intensive or intractable task. Fine, you have exascale, you have supercomputers, but still you will not be able to crack it, because you have a shelf life of billion of years. Okay, so what we thought is we are already secure. The other way is the quantum security, which is through a physical device, or using the laws of physics to break it, to safeguard it. And this is our approach. Interestingly, and I don't want to keep on, have more slides on that. We know that there are certain mathematical intractable problems. For example, prime factorization of a composite integer. It's considered to be hard, and it itself, the problem, the problem statements, to identify them as hard is very difficult because there is no proof. But anyway, so we were looking at the RSA, or the factorization problem. Now, no one actually considered the potential of a quantum computer that time. Okay, so and it is found that I think you must have already covered the computational complexity classes. So there you will find that the factorization problem is solvable in polynomial time, and through a quantum algorithm known as Shor's algorithm. So now what appears to be secure, I mean, it's all our money, it's national secrets, it's critical, strategic areas which we are talking about, all will collapse if somebody is building a quantum computer, because a crypto cracking quantum computer, say in about 10 to 15 years, would be able to perform Shor's algorithm, okay, and solve those problems and fetch the key. And so if you have a cryptogram which you can always keep on saving, if there's an encrypted data, you keep on saving it, and then you are able to get the key out of it using Shor's algorithm, and you will be able to have access to the classified information. And that is the reason, you will see political parties and national recognition of this upcoming or this transition, I would say. So now the shift has gone from mathematics to physics. So we say there are some rules which we will discuss in this session. No cloning, non-locality based on entanglement. If you're doing any perturbation, then we are knowing that somebody is eavesdropping. Because the only difference here is, in classical communication, you are actually encrypting information on millions of photons. But in quantum communication, I will be encoding information on one photon, which is a quantum entity. So whenever I'm encoding on a quantum entity, it becomes a quantum encryption. And when I'm using communication, such a communication, then that is a difference between a classical and a quantum communication, that I'm communicating using quantum entities. So now, is this discussion a reality? Oh yes, we have products in market. We have QNU Lab, SETS, then ISC, DIAT, IIT Delhi. There are so many organizations in the national ecosystem players who have made TRL. I would not say exactly product, but yes, TRL 6 to 7 level prototypes, working prototypes, through which applications can be ventured. And you will see the global players also here. So now there is so much happening. The transition is happening. There is a mandate by the government, by US and UK, to transition to post-quantum cryptography, which is nothing but a mathematical approach. So instead of factorization problem, we are looking at those problem statements which is still intractable, or which cannot be solved using a quantum, or which is believed to be not solvable on a quantum computer, because again there is no proof that it belongs to proof that it is a hard problem. So that is why a rigorous exercise was done by NIST, and they have come out with some standards. And now there are vendors, there are hundreds of global vendors who are actually who's actually transitioning to post quantum cryptography. But then why not QKD? Now there was a paper by established national bodies on the position on QKD. Some say it is not sufficiently mature from a security perspective. And so we need to understand, why it is being said. It is technology limited. And there are so many comments. And since I have been working in this area, so it was very interesting to understand why is the objection, what is the objection, and how can we, work in that direction. So when you say it is technologically limited, what does that mean? We need specialized hardware. I mean, if you have seen my other presentations, we had shown, single photon detectors, which are only 10% efficient, which works under special conditions of light, humidity, temperature. They are extremely expensive. Then the distance limitation and end-to-end security. You cannot go more than about 80 to 90 kilometer unless there are some breakthrough QKD protocols. And people are looking into satellite communication, integrating terrestrial to satellite, to having quantum relays as aerial platforms to create a link. So this is a challenge. Then reliance on classical cryptography for peer authentication. Of course, we in quantum key distribution, we are only solving the problem of having symmetric secure keys in the presence of an eavesdropper. That's what we are looking at. So the concerns are genuine, but we need not succumb to it. It can be addressed with good engineering and a very good understanding of quantum information science as well. And why they say that it is not mature? Because there are no standard QKD protocols. And after this session, you will have an idea of what this means. The security proofs, they are good on paper, but we have a lot of security, we have a lot of loopholes, which is okay, because still now we are fixing loopholes in classical cryptography, which is 70 years old, 70 to 75 years, a little more perhaps old. So QKD is fine. We are just, we are getting started. The evaluation criteria and methodology needs to be developed. So this is I'm trying to bring this to you because you need to have a bigger picture as well, and to understand that how you would want to contribute in this area. There is a huge potential. And as you can see, these questions, and I think the community I'm talking to is actually will try to address those questions, technical questions. Fine. So, you can just go through it, but these are on the similar notions. And I had a chance of talking to a student of Renner and Miss Wolf, and they had given a paper on a rebuttal to the NSA's objection, and they're hardcore mathematicians come physicists, and these are some of the arguments they had presented to this. So what I'm trying to say is that there is a debate going on. We need not think that PQC is the only way. QKD has a way higher chance, and there is a national adoption of this technology which is also happening. Okay, fine. And so again, these are on similar lines, but let me skip it. So why we are so sure about the security of quantum key distribution? Okay, so again, when I'm saying here quantum key distribution, it is different from that of classical key distribution, where I'm generating the key and sending it. In quantum, I am generating secure, symmetric keys. I'm using each and every word with responsibility. The word secure comes from some mathematical, developments or formulation which happens. Then key is the key which is getting generated at transmitter and receiver end simultaneously. There is no key transfer. Okay, and the word distribution is, it is getting shared between the two parties without the key actually having to travel between Alice and Bob. So the keys are getting generated, and we will get there, I think, in the second part of the session. We will discuss about in more details about a quantum key distribution protocol. So now the first part is the first preamble. So there are some ideas on why do we have to believe quantum mechanics. What are those laws which actually helps us identify or helps us to safeguard communication when I'm encoding information on the qubit. Now, there is this excellent book by my supervisor, PhD supervisor, Professor Anirban Pathak, and the book is actually a good beginning itself. It talks about the elements of quantum computation and communication, and I would suggest, I highly recommend. I still carry this book. Whenever I have some some doubts or some clarifications or revising my basics. So this is a good material. Well, coming back to the basic notion of what is why should I believe that my information is secure, whatever I'm encoding. So one thing is that there is no quantum Xerox machine. Okay, so if you can consult, so the law says that, or the theorem, that there is no unitary operator that can clone an arbitrary qubit. Now, if you remove the word arbitrary, it is dangerous. Please don't do that. So when I'm saying it cannot clone any arbitrary qubit, it has to be taken as it is because of the maths which we will now investigate. So basically, you do not have a quantum Xerox machine. What does that mean? That if you are having, say, ket xi, some state, okay, and say this is your white blank paper where you would want to copy the state onto this blank page. So you insert a blank page and you insert the document which you want to copy in a quantum machine, quantum Xerox machine. So now actually this Xerox machine is an operation, and it is designated by a unitary transformation, which will given or which will duplicate a given arbitrary state. So under no circumstance, that you will be fine the arbitrary state getting duplicated. So this is not possible. So this is what the theory talks about. So what does that mean? That if I'm encoding a key, because my key is a qubit, it can be represented by ket phi. So there is no Xerox machine where I'm putting a qubit and another ancillary qubit, and the state gets replicated. Okay, so in order to prove this, we will begin by saying that let there be such a Xerox machine. Let there be such a unitary transformation which can duplicate a particular state. Okay, now you can see equation 1, that is what I mean mathematically. And these are tensor products, tensor sign. So now, if there is a universal Xerox machine, then it should be able to copy another state as well. It should not be, it should be useful. So it should be able to duplicate another state, say cat5. So the output should be cat5 tensor cat5. So it's a duplicated state. Now, now what we'll do is we'll take the inner product. So this, by now, I think you understand what is an inner product, and this is how it looks. We have bra xi plus and cat5. Okay, we take the inner product, and what we find is we get square of mod of bra xi and cat5. Now, if you look here, that this equation gets solved if is satisfied if we get either 0 or 1. Okay. Now, this could be 1 if both the states are identical, and if this could be 0 if both the states are orthogonal. So I'm going to make a very important statement that therefore both cats xi and cat5 cannot be arbitrary, which means that if there is a machine that can clone a particular state, then at best it can clone another state which is orthogonal to it. Hence, cloning an arbitrary state is not possible. So this is the idea. Okay. So again, I would say when I'm doing a classical communication, I'm having millions of photons in a pulse, right? So I can replicate that state as well. But when I'm having one photon in superposition of many photons, it's very difficult for me to replicate because of the superposition, random wave function collapse. You know, I hope you must have now get familiarized with these concepts, you know. So these are the basic nature of quantum mechanics or quantum entities, superposition and entanglement, and the maths behind it, which actually provides this framework such that you cannot clone an arbitrary quantum state. So this is one thing. Next we have is the non-orthogonal states. They cannot be discriminated with certainty. So far we have known that the no cloning theorem is the basic idea of cryptography, right? But in 1960s, in a paper called "A Single Quantum Cannot Be Cloned," Wouters and Zurich had come out with an idea of quantum money. So this paper gives you the formal introduction of no cloning theorem. He said that you have the quantum money which cannot be forged. He used the ideas of non-orthogonal states in quantum cryptography. So here you have seen, here I have drawn the two non-orthogonal states, ket xi1 and ket xi2. So mathematically, we interpret it as that the two, we say that the two non-orthogonal states cannot be discriminated. Again, I'll have a few slides on this particular concept. But here it means that, you know, that ket xi1 and ket xi2 are the two non-orthogonal states. Then any one of them can be decomposed into a non-zero component, parallel and orthogonal, okay, to the other one. So then this creates an ambiguity, and this leads to the to monitoring the performance of the communication system. So as and when somebody is trying to monitor or tamper with the system, because of this ambiguity or uncertainty, the performance is impacted. I get a high error rate, the throughput decreases, and that gives me an indication that somebody is actually monitoring the channel. Then we come to the concept of non-commutivity. So what do we mean here? I hope again you are familiar that in quantum mechanics, we for every observable, like position and momentum, which I have mentioned here, you know, energy. So they are all operators. There is an operator for each and every observable. as you can see here, the position momentum in x direction and the momentum operator in x direction. Okay. Now, since both these operators will not commute, therefore, we are not able to measure them simultaneously with arbitrary accuracy. Okay. And so this non-commutativity, non-orthogonal states, these all come together, and no cloning. So these all come together to protect the quantum information. Now, this concept which I'm presenting here, I think you are all familiar, because this forms a basis for not being able to simultaneously detect the wave and particle nature of electron, right? So it's the same. So the maths of that says that the commutators, the operators, they actually do not commute. Okay. Now, again, applying this uncertainty principle using some nice pictures here, a short story, I would say, that Alice is trying to communicate with Bob. Okay, and they are communicating it through some electrons. It is passing S1 or S2, some binary information. So electron gun is randomly emitting the electrons. Okay, and before a metal wall, the metal wall has two slits, S1 and S2, and beyond the wall is a layer which will be absorbing these electrons. Now, if I am closing, so these are the openings, right? And P1, P12, P2 are all the probability density patterns. So P1 is the probability density pattern when S2 is closed and S1 is open. And P2 is the probability density curve when S2 is open and S1 is closed. So you can see a bell curve. So this is a classical signature. Now, when both the so now when both the slits are open, what we find is a quantum signature, which is an interference pattern. So Bob is able to identify that it's coming from Alice and there is no eavesdropping, because he's able to see the classic of quantum signature. Because had there been an adversary, the quantumness would have gone, the quantum feature would have gone. So this is what happens here. So when Alice, so if there is an eavesdropper, and this is very well described mathematically and in Feynman lectures. So why we say it is quantum, and it's a quantum curve, how it is different from a classical signature, it's very well explained. Now, what it tries to say is, if an adversary is trying to look into the electron, then he does a measurement on that electron, right? And he disturbs that state. And the moment he disturbs the state, then the quantumness is gone. The property collapses to one of the possibilities. It is no more in superposition. So when you're losing the quantum signature, you get a bell curve, P12, which is a classical signature. So if you look at if there is an adversary trying to see whether the electron has gone from slit 1 or slit 2, then accordingly, if both the slits are open and he's trying to look into it, then the quantum signature collapses to a classical signature. So this is how Bob comes to know about the quantum key distribution. Whether in quantum key distribution, the same thing happens. If Bob is getting whatever Alice had sent, okay, and he observes, say, a Q-bar which is within the range. Now, why would I say within the range? Because there are several. If you see the QKD, there will be several processes involved, which again I'll be talking about in detail in my next session. So there will be a lot of processes involved there, and there are optics, there are electronics, there is synchronization software and signal so a lot of things happen, and it's not ideal. So it leads to a basic threshold voltage error, which will be of the order of, say, something about 3 to 4%. Even in the Indian standards, the QBER, which is actually prescribed, is less than 5%. And we will see that, if you look into the quantum key distribution key error rate, if you start increasing the error rate, and you will see the ratio of secret key with respect to the distance, you will, or the error, you will see that these, as and when the key error increases, the secure key length also decreases. So when error means that you are actually dissipating a lot of information from the system. And in quantum key distribution, you have a classical adversary, but let me forget the classical adversary. You're working with a quantum adversary, which has all the powers of quantum physics. So he can take one photon, he can study it, and he can keep it back if the physics allows him so. If there are two photons, then he knows, if he picks one, you still have one photon, then he can pick that up and measure. So he has got all the powers of quantum technology. So considering all that power, I am actually reducing the secure key rate in a fashion, considering that these are my loopholes. These are the loopholes because of the algorithms I'm using. So this much amount of information can be leaked to the adversary. So what is the mutual information left between the sender and the adversary? Okay, so based on that, I'm subtracting that mutual information from the final secure key, and then I'm getting it. So if I'm having a lot of errors, the information between the Alice and the adversary will be higher. So I need to do more subtraction. So in that manner, my secure key keeps on decreasing. So though I have described this in a very simple format, that if there is a disturbance, then the quantumness is not there. But when you're talking about the actual system, the disturbance comes from different angles, from the environment, from the ambience, from the parameters within the product, like temperature, light, ambient light, vibration, mechanical vibration, electronic. So there are multiple sources of error. Now, because of that, it doesn't mean that each and every photon is getting collapsed. Okay, so it can get distorted. It can get it has to be purified in from that perspective. So fine. So then we move forward. So now we are actually differentiating the quantum transmission, or a QKD, into two parts. One is the um, prepare and measure part, and the other is the detection based method. In prepare and measure, I should have drawn some figures here, but if you can visualize, you are actually preparing the sender, or Alice will prepare the state, quantum state. He will encode some information on the quantum state, and then he will send it to the other party. If you just consider this part, Alice and Bob. Yeah. So here Alice will have a quantum state generator, which will generate quantum entities. We will prefer using photons because I have to actually communicate from one point to the other. So you have quantum state generator, then depending upon the nature, you will be having a quantum encoder, and then you will be sending the data from here, from the sender location to the receiver location. So this is prepare, and Bob is measuring. So this is prepare and measure. So the protocols are BB84, DPS, differential phase shift QKD, or differential phase reference QKD protocols, round robin DPS QKD, time encoding QKD, so B92 QKD. So here again, those protocols, Alice is preparing the state, Alice is encoding the state and sending it through either by a fiber communication, or through a I'm so sorry, or through a free space communication. Okay, and then Bob is measuring that state. He's converting it from analog to digital, and both will be getting some shared, partially shared binary numbers, and from that they will be processing the final keys. So that is prepare and measure. In the next session, we'll be talking about the BB84 protocol. Bennett Prasad, 1984, developed proposed protocol, which is again prepare and measure. Okay, so now this thing should be very clear. The second protocol. Now, again, when I'm talking about these rules, let me tell you also that in prepare and measure, the security principles will be based on no cloning. Okay, so no cloning theorem and non-orthogonal states. In BB84, in B92, in DPS, in round robin, I mean, all of these prepare and measure states, they definitely they are using, you know, no cloning principle, non-orthogonal states, non-commutativity of the non-orthogonal states, you know, as a basis for quantum communication, secure as a basis of security for quantum communication. Then the second is the entanglement based. So what is that? How does it look? So instead of the QKD, this orange box, consider a transmitter. Okay. So you have entangled photons are two particle states. Okay. They behave as one, but they are two particle states. Prepare and measure, you have single particle, single photons. Okay. Or a weak coherent source nearly in the quantum regime. Now, in this orange box can be a transmitter sending two entangled photons, one coming in box 1. Just think this is box 1 instead of prepare and measure, and this is box 2. So this is Alice and this is Bob. So you have entanglement photons coming out from this orange box, and one photon is going to the box 1, which is Alice's box, and the other photon is going towards Bob's box. Okay, you may also would want to consider keeping the transmitter and Alice in one node, okay, and receiver in the other node. Now this is how some of the experiments have been done by national players as well. However, we are actually working in the entanglement based protocol in tri-party. So we are using the transmitter located in some place. Then you have receiver 1, which is Alice at some other place, and receiver 2 at some other place. Okay. And we use non-locality, something which I have not mentioned here. I will discuss tomorrow. So we called it non-locality as the basis or as the pillar of security of quantum communication using entanglement based. So I hope this slide is actually very important, because this you'll be using it most of the times if you are trying to build the experiment or you are trying to buy one QKD. Prepare and measure, there are two boxes. One prepares the state, other measures the state. Okay. Then you have entanglement based protocol. One generates the quantum entangled photons, say Charlie, and then you have two receivers, Alice and Bob. Once they have the entangled particles, these two receivers will be talking to each other to generate the entangled, to generate the keys. Okay, so it's very interesting. Charlie is sending, receiver 1, receiver 2 are only receiving, but they will be communicating in a manner such that they generate binary keys from the correlations. So one question comes is, if I'm not actually sending the key from one place to the other, then how am I generating the keys? How am I getting the keys? So actually, using superposition and entanglement, I'm using correlations. Okay, so based on that correlations, I'm deriving the key in the entanglement part and also in the prepare and measure. Because of superposition, and there is also some correlation there, which I'm using to measure, to derive the key using prepare and measure. Then we have here detection method we discussed. So There's another thing also which the community should be looking into is the photon statistics. In entangled based method, the source is the we generate the entangled photons through nonlinear process. In prepare and measure, we again generate the source using a nonlinear process, as well as use attenuating the laser in the till I go to the quantum regime near about mean photon number 0.1 or 0.2. That is 1 photon in 10 pulses, and I do not know where the photon lies. Okay. So, so these two are very different based on the generation of source, based on the encoding principle, based on the topology, based on the security which gives you the quantum, safeguards your communication. But while detector will be same. These are single photon detectors, because single photon detectors is irrespective of whether it is a entangled photon, or it is a single correlated photon, or it is a weak coherent source. So the detectors are always same, but we divide the detection based on discrete variable and continuous variable. So there are homodyne detectors based on for continuous variable QKD, and there are discrete single photon detectors for detecting single photons. But again, it is tricky because a single photon detector cannot actually detect only one photon. It can detect 2 or 3 photons together. So it cannot differentiate between 1 photon or 2 photon. Then there is another thing called photon number splitting detector, which does that job. So you need to distinguish between these two categories: detection based. In some of the research papers, it is done primarily on detection based, and in standards or while preparation, thinking about a QKD, you will think about these two categories. So I would like to end this session here, because in the next session we will study the elements of quantum key distribution, and we'll pick up one of the protocol, BB84, and study that in detail. So if there are any questions, so far, then I can address that. Okay, I hope I was okay.
Yes, ma'am, there are some questions. Should my student dictate for you, or you can see that?
Okay, just let me.
Okay.
Yeah, the last question I can see by Himani, madam. So in the beginning, you had mentioned that secure key is locally generated and it does not travel between Alice and Bob. Yes, but when you're explaining, you're mentioning that about the key traveling from Alice to Bob via optical fiber. Yes, so this concept is very important. When I'm saying that the key is generated in the classical world, I'm using some PRNGs. Say, for example, I'm using a PRNG to generate one key, and then I'm sending it from one point to the other, writing on a mathematical statement. That is classical. In quantum, I am generating some quantum states. I am encoding those quantum entities randomly. Okay. So far, there is no key. I'm generating some random numbers and encoding them, because finally I have to fetch the data in terms of zeros and ones, right? So I generate them, and I'm sending them. I have generated millions of say encoded quantum entities. I keep a table. My first I have to do this with respect to some timestamp, perhaps, that my first pearl I had used random number 0, where I have changed its state from horizontal to vertical. So like that, I'm creating a table, and then I'm receiving the photons, encoded photons. Okay. And then the encoded photons I'm receiving in only thousands. I'm sending millions, I'm getting thousands. Why? First of all, my detectors are 10% efficient. Then the fiber attenuation is there. Okay. And there will be some absorptions also along with it, other than because there are a lot of optics around it. There is an interferometer at the measurement side. So some more additional optical delays will happen. So I'm sending those photons. This is called quantum data transfer. After that, Bob and Alice will start talking to each other. I received this. I received I received a state with a timestamp. Okay. They don't say what they receive, because what is the key information? They say that I received something in this timestamp. Then Alice will find out, from that conversation that, okay, so what did I send during that? So she will be doing some maths and she'll be deriving that. In this manner, they extract the partially correlated binary keys. Okay, that is called the raw key. Then they will do another process called sifting based on the protocol. So let me leave it aside. Then we do error correction. Okay, so from partially correlated to we go to perfectly correlated. Now I know that there is a caution. There is no error correction algorithm which can give me 100% efficient error corrected keys, right? So then there comes a step of, at the end, I do error key reconciliation as well. Okay. And in between there is a privacy amplification. So all that things I will talk about it in my next session. So this session was important to understand that there are some security principles which is specific to prepare and measure, and some security principles specific to entanglement. Why entanglement is very interesting? Because we are actually doing non-locality, non-realism. That's why the security is more hardened theoretically and experimentally. And the notion of device independent QKD comes from entanglement only. Okay, so the deviation of classical key distribution with respect to quantum key distribution, where I'm using physical device to create quantum states, send them along. I see where the wave function has collapsed, because a wave function collapse is random, and that is an indication of the key. So that then I'm forming key. So before that, I'm not forming key. I'm only doing a data transfer. So the key starts forming when I'm getting detections or I'm filtering them out. Then that is my first key, which I say raw key. Okay, so then the next question is IIT QRNG. Okay, so see, there are whenever, let it be IIT, it can be DRDO, it can be DIAT, it can be CDOT, it can be TACBIT. There are so many companies which are coming out with quantum random number generator. So in any case, you should be focused on what is that quantum noise or quantum source which makes it quantum, whether it is a classical process. Okay, now the classical process with, sometimes there are quantum process with a classical signal, because we are looking at the quantum property. So what is that quantum in that random number generator? That has to be questioned. Okay, so I will again suggest, because the paper is not yet out, I'm not aware, but it's a fantastic job, because all what the market uses is a small form factor, a high throughput. And what IIT Madras has done is, making the reducing the form factor, improvising on the throughput, is a very good step in that direction. Then we have, how do we distinguish between the keys generated by quantum computer and a classical computer? So classical computer is simple. You are processing some algorithm, right? It is algorithm driven. It's known as pseudo random number generator, the one which has its dependence on the seed. Okay. In quantum computer, okay, there are some groups which are using the Qiskit or maybe the IBM quantum computer, and they are doing a non-locality testing or generating, quantum random numbers along with it. It's fine. I mean, it's an experiment. It's fine. But the thing is, if you see the practical utility, it has to be within the device. It has to be of a higher throughput, because since 1970s we have QRNG, but that was for the based on the principle of radioactive decay, which gave you 5 to 6 bits. So now if you are having a big machine which is saying that you have a ultra high secure QRNG, but it is so big that it cannot fit in, what is the purpose? So we are looking into QRNG because QRNG has a higher throughput. Radioactive decay based QRNGs, chip size, they go till 10 to 11, 12, or maybe 20, 30. You can design in a manner that you can fetch more, but not more than say 50 or 60, right? But in QRNG, you can actually go in gigabits per second. Some of them, most of them are actually Gaussian, but then there are ways to extract the quantum randomness out of it. And that is why you will always have a post-processing. Any physical random number you generate, you will always have a post-processing module to go along with it. So I hope that brings some clarity. The role of environment in key distribution, very, very important, because you are actually sending quantum entities, which is fragile, which is picowatt 10 to the power minus 12 watt. So if I'm doing a quantum communication, I am actually sending my photons. I'm using light because otherwise I cannot send from one place to the other, from here to the satellite. How will I send if I do not use photons? Now, photons are a good candidate. It can travel. It is also robust, but it is either through free space or through fiber. Both has its own challenges. So I'm using my encoding wisely and seeing how much fragile is my encoding with respect to the communication medium. It's that way. So yes, as Ankur is saying, noise, turbulence, distance with free space, particularly aerial QKD, atmospheric turbulences, diffraction, dispersion, all that things are there. One has to take care of depending upon which medium you are using. And there are some very good simulation tools to find the performance of a particular QKD with respect to distance and with respect to environmental conditions. I will suggest using right now it's not coming to OptiSystem. We use OptiSystem to simulate the optical components. You can also use some other tools to see for atmospheric conditions. You will not have a quantum state generator in those tools because, but then you can create some mathematical functions to generate. So that should be a possibility. Then you have what are the possible attacks for QRNG? Possible attacks, yeah. So one of the attacks can be to malfunction the detectors, to introduce biasness. Okay, so that is one of the, I can introduce biasness either by playing with my voltage levels or with current levels, with deteriorating the performance of my detectors. So I will not be getting my symmetric zeros and ones. They will not be uniform. So there are ways to tweak and see the performance of the QRNG based on the these imperfections. Open QKD tool, fine, yes, this is also good. So now I think I'm supposed to take 5 to 7 minutes of a break before I jump into the next session.
Yes, yes. We can take 5 minutes break, ma'am. Thank you very much, ma'am.
Thank you.
Yes.